hear this? All right, let me just start the recording. And let's look at number 11 here for chapter 29 for you, 122 people here. All right, so let me skip over to the questions. Let's see, before the break, where were we? Oh yeah, we were on 42, so it'd be up a little bit. Number 11 says this: a proton, which has a charge of plus E and of mass m sub p, and a deuteron, which has a charge of a plus E and a mass of 2 times the proton, and an alpha particle, which has a charge of 2E and 4 times the mass of a proton, are accelerated through a common potential differences of delta V. All right. Each of the particles then enters a magnetic field, B, which its velocity in the direction that is perpendicular to B. The proton moves in a circular path of radius r sub p. Determine the radii of the circular objects of the deuteron and the alpha particle. All right. And so, by the way, this is kind of the fundamental working of the mass spectrometer. We have different particles. If I start with this idea of the proton is just that. It is made out of one single object, which is a proton. I'll draw a little picture like this. Whereas the deuteron is what we call a composite particle, because it's actually made out of a proton and a neutron. And a neutron and a proton have about the same mass. So this would be saying then that if this is the mass of the proton, the mass of the deuteron is twice that of the proton, because it's actually made out of 2 nearly identical things, a proton and a neutron. Now, in terms of charges, the proton has the same charge as the electron in terms of magnitude, but it does differ in the sign. So an electron is negative and a proton is positive. So the deuteron would have just one charge from the proton, because the neutron is called a neutron because it's neutral. And so the deuteron just has more mass than the proton, but same charge. Now, an alpha particle is actually then 2 protons and 2 neutrons. So because of that, it has a mass of about 4 times the proton, because it is essentially made out of 4 objects, each having the same mass. And of course, now it has then 2 E pluses for its charge, because it's got 2 protons inside of it. And so that is something that they're trying to explain in the question. They don't expect you to know that, but I thought it would be a good place to kind of get started and just say, okay, what are these objects, the proton, the deuteron, and the alpha particle? Now, they say that they're all accelerated through the same potential difference. And here's what they mean by that. What they mean, in this case, they're all positive. So if you took a metal plate and made it negative, and for this to work well, you have to kind of put a small little hole in it. So it's almost a solid metal plate. There's one small hole, because over here somewhere, and without going into detail, you generate these particles. And it could be a proton, it could be a neutron, or it could be an alpha particle. But as this particle comes off, it is usually barely moving. And so we would say it has some initial speed pretty close to 0. You just kind of break it free. But you see, because it is positive, and all three of these are positive, it would get pulled over towards this negative plate. So this thing, and there would be billions of them. Actually, that would be a small number. Trillions, that would be small. Quadrillions, no, that would be small. Quadrillions of quadrillions. Okay, so good thing they're small, and quadrillions of quadrillions is not unreasonable. And as they get pulled over, some of them will have, and most of them will have an initial velocity that will make them miss the hole, but there'll be a small percentage, let's say 0.001%, that will be heading in the right direction. And then they are accelerated by this negative charged plate. And they actually then fire through this hole and come ripping out this hole at some, I'll call it the final speed. So that's how you get them accelerated. So that's what it means here when it says they're accelerated through a common potential difference. And so this is actually then hooked to a battery of some type. So positive and negative. And they're saying this is a voltage of delta V, and usually in the tens or even hundreds of thousands of volts. They, and this one, do not say what it is. I'll just write it as delta V. But that first part right here can give us a clue to how fast they will be going. And so this is what we refer to as a gun, a particle gun, because we can make particles, charged particles. Sometimes they're electrons, so we call them electron guns. Sometimes they're protons, so we call them a proton gun. Sometimes they're alpha particles, we call them an alpha gun. But this particle gun is kind of an overall name that we say gets these things going really, really fast. And of course, you can imagine how fast would be dependent on, the charge on this plate, which is what's accelerating them. So let's do that first. Let's see if we can figure out how fast they're going. And I'll use that really going back to Physics 121 and conservation of energy. And we can kind of split the paper and say the initial energy is equal to the final energy. And if we then, as a reference, kind of like we did with gravitational potential energy, Physics 121, mgy, we could set y equal to 0 wherever we want. So same thing with the potential. That's why I'm sure they just call it a difference. They want to say you can call 0 wherever you want. So maybe I'll do this. Maybe I'll call where this connector is hooked to this plate, I'll call it the potential. So that potential would be 0. And that means over here where it got started, the potential would be delta V. It has increased from the 0. That's what they mean by the delta V. This battery is increasing the voltage, the potential from here up to here. Now, here's why that's important. If I say, okay, what's my initial energy? Well, maybe I'll have part of it is the initial kinetic energy, and part of it is the initial potential energy. So again, this principle is conservation of energy, and they are equal to each other. And then one of the things, again, we learned in Physics 121, besides conservation of energy, is that the kinetic energy is 1/2 mv squared. And like I said, if you have some kind of mechanism here that just breaks them off, they're barely moving. And so what we can say is here at the beginning part, what they have is some electrical potential energy. The analogy would be holding a ball up on top of a building. I'll just take my pen. If I took the pen and I held it up at the top of a building, I would start here with an mgh or an mgy and say this is the initial gravitational potential energy. In this case, I would say these particles have an initial electrical potential energy. Because again, as they go over from their starting point to, I'll call this their ending point, although the truth is they're not ending. They still got to go into the magnetic field they're talking about. But this is the part that is the first half of this problem. They accelerate them. So they would now have a 1/2 mv final squared and a qv final. And of course, the way I set it up, you didn't have to. Remember, I said you could set the potential energy equal to 0 anywhere you want, just like when we did our gravitational potential energy in 121, we could set our y equal to 0 anywhere we want. Now, usually if we're dropping something, we call up at the top the y and down at the bottom 0. So we usually call the bottom 0, but we don't have to do that. We could have called the top 0, and then as the ball falls down, then its final position would be a negative position. But the way I set it up is a lot like calling the starting point with a lot of potential energy and the ending point with no potential energy. So if our final potential is 0, then this has to be equal to 1/2 mv squared. So if we rearrange this, we can see that the velocity, so hence this gun, this particle gun, would give these particles a velocity based upon this equation. There would be a 2, there would be the charge of the object, there would be the voltage that it was accelerated. We would then divide it by the mass, and then taking the square root of that. This here would be the equation for how fast there would be going. Now, to be quite honest, I don't think you need to redo this equation like I just did for this problem. It's been done in a number of other problems and in the book. So I think I grabbed the Survey textbook. It's probably a little bit at the beginning of this. In applications, maybe it's a little further back.
Hey, Professor, I'm just wondering, I just jumped in here. What question are we on?
Oh, we are on question 11.
Gotcha.
Yeah, perfect. Well, maybe I shouldn't take time, but I thought the author worked this out in a number of places. And maybe it's right here in this example. There it is. And so in example 29.3 on page, it looks like 815, the author did it here, and I think a few other places. Whoops, got out of the camera right there. So that's the equation I got. So what I guess I am saying is I hopefully am just adding more and not taking too much unnecessary time, but you don't, I think, need to do this. And if it was like an exam question, you could just start with that equation. And so we really haven't even got to the heart of this question. So I think the author is saying, look, using that equation to figure out how fast these particles are going, I think is fine. So let me call this page 1, and I'll come back to that equation, I think, real soon here. And come over here to page 2. Because now we get to the heart of this problem. And so let me go back to the reading of the question. It says here, they're accelerated through a common potential difference. Okay, and so here's the big sentence. Each of the particle enters a uniform magnetic field of B, and its velocity is directed perpendicular to the magnetic field. The proton will then move in a circular path. Let me just add, all particles that are charged in a magnetic field will move in a circular path. Maybe I should prove that to you again. But that again was shown in the lecture and in the book. The proton, it says, determine the radii of the other ones, the deuteron and the alpha particle. So let me just kind of take this particle and say, okay, it's moving with some velocity, which I've called V final. and it enters this space over here that has a magnetic field. Now, if I make the magnetic field pointing out of the screen, in other words, towards you guys, and maybe I'll just do a magnetic field in, I think your book had color coded the magnetic field. Maybe I should try to match that. Oh yeah, he does green. So I didn't do that before. So I'm gonna try that in green here. So making the magnetic field pointing outward with a dot, and so green with a dot, and I'll put a little B. There would be the magnetic field. And the heart of this problem is that there is a force, a magnetic force, we like to say, on a charge moving in a magnetic field. So you probably heard me say in the lecture that this is the fundamental principle of the chapter. Now, let's talk about this, because there would be I'll call it 2 steps to this. One step is to figure out the direction of the force, and the other one is to figure out the magnitude of the force. Let me start with the magnitude of the force. Again, this takes us back to physics 121. In 121, we learned things like A cross B equals vector C. And that goes way back all the way to, I guess it's chapter 2 in physics 121. You guys did cross products, and then you used it to do things like torque. Torque was R cross F. Oh, and actually, that'd be good for me to remind you, because there is a torque question in number 35. There's a motor question, so there's more torque. Angular momentum was another thing we learned in 121. I don't think we'll need that one for this chapter. But those were 2 cross products. So when the author gives you this cross product, he's saying, remember, to get the magnitude, you take the magnitude of the first vector, the magnitude of the second vector, and the sine of the angle between them. So in this problem, the V is going horizontal. I'll call that the x-axis. If we kind of use the traditional grid of calling to the right the x-axis and the up the y-axis, and kind of out of the paper or out of the screen towards you as the z-axis. Okay. My direction of the velocity is then in the x direction. And the field in this picture would become out of the screen, so it would be in the z direction. And those are 90 degrees to each other. And sine of 90 degrees is just 1. So the first thing I'm going to do is get this equation. This would be the magnitude of the magnetic force. The other thing for me to remind you about cross products is how to get the direction. And we have this fancy thing called the right-hand rule for vector cross products. And this morning I was warning students, so I want to warn you guys too, that there are more than one right-hand rule, even though right now you've only been exposed to one of them. And because of that, there's a temptation just to call it the right-hand rule, but that can get confusing later on when we have more than one. So let me call it the right-hand rule for cross products. So again, last semester, you learned it to get torque and angular momentum. Now this semester, I'm going to have you use that to get the direction of the force. And as you'll see in the next chapter, I'll give you 2 more right-hand rules. So I don't want you to confuse them, although those 2 could be thought of as one. So by the time we get done, you're going to say we have another right-hand rule or 2 more right-hand rules. But in either case, make sure that you say, and I always say, this is the right-hand rule for cross products. And if you remember that rule, it goes something like this. You take your right hand, and the first thing you do is you put your fingers in the direction of the first vector that's listed. So in here, that would be A, or in here, that would be R, or here, that would be R. But for the problem we're interested in, that would be the V. I'm going to put my fingers in the direction of V. So I need to turn my hand around, and I'll do that in just a second. But I also then need to adjust my wrist so that when I sweep my fingers closed, they sweep towards the second vector that is listed, which for us, it's going to be B. Back here, this general one would be towards B, or this would be towards F, and this would be towards P. And we're going to want it towards B, the magnetic field. All right. So let me take my right hand and get my fingers in the direction of V. So I guess that means I need to come around and do something like this. So I got my fingers going in the direction of the x-axis. Now, right now, if I sweep my fingers closed, they go towards a vector that would be pointing up on the screen, and that's not where magnetic field is. Let me point out, remember, magnetic field is going up. All right, so I'll get my fingers back in the direction of the velocity, the first one listed. But now I need to rotate my wrist. So it would look like this. So now when I close my fingers, they're closing towards B. All right. So fingers towards V, closing towards B, that's good. So my thumb is the direction of the cross product. Okay. So as this particle enters, V cross B would be down. Now, that's not necessarily the direction of F, because remember, when you multiply by Q, and Q can be either positive or negative. So V cross B is down. If I multiply that by a positive charge, it's still down. But if I multiply it by a negative charge, it would be up. In other words, it would be the opposite of down. So I want to emphasize V cross B is not necessarily the direction of F. You've got one more step to do, and that is multiplying by what kind of charge you have. Do you have a positive or do you have a negative? Now, for this problem, all three of ours, if we come back to page 1 to remind you, all three of them are positive. So we're going to be multiplying by positive charges. Okay.
How did you know that what direction B was going in? How did you know it's coming up?
I guess I don't really know it's coming up. I had to pick one. All I know it had to be perpendicular.
Okay.
Yeah.
Well, if you pick down, wouldn't that change the direction of the force?
Yes, but it would then also change the plane of rotation, but it would still be the same radius, which is the question.
Okay, gotcha.
Yeah. So you're right. If I had picked B down, I guess my hand would look something like this. I would go V cross B, and my thumb would be pointing inward. And so the charged particle would curve downward in. And I couldn't draw that real well. So that's why I didn't do it that way. But it would still make an arc, but it would be going, into the Z-axis. Whereas this way, by drawing the magnetic field out, it would arc around like that. Now, again, here's where a little bit of physics 121 still needs to come into play, because remember, when it enters, the force is down, which changes its direction. So when it gets, say, to here, the velocity is down and the magnetic field is up. So velocity is down, magnetic field is up, and the force would now be this, which would turn it again. And here's the part that I was saying, physics 121 needs to come back into play, because what we learned in chapter 6 of physics 121 is if you have a force that is perpendicular to the motion, it will not slow it down. It will not speed it up. It will only turn it. And it will turn it in a circle of constant radius. So I'm taking advantage of that from physics 121, because you see this cross product? This cross product is really saying, when I do this little hand thing, that the force will always be perpendicular to V. See, if you always put your fingers in the direction of V and you close it towards B, this thumb is always going to be perpendicular. And so I know when I write this equation and I read the math, if I can use that phrase, reading this math tells me that the magnetic force is always perpendicular to the velocity. And then going back to physics 121, a force that is perpendicular to the velocity, excuse me, a force that is perpendicular to the velocity will always make it turn. It won't make it go faster, and it won't make it go slower. So this thing will go through and always turn, and will never go faster, will never go slower. And in fact, that's where this is going to come into play, is physics 121, because I just calculated down here the magnitude of the force, the magnetic force. And that has to equal to mv squared over r being the radius of this circle. So that step right there, that's the centripetal force. That's the physics 121 that says if you add up all the forces, so this force, the magnetic force, is the only force when it is moving through this magnetic field. So if you add up all the forces, you have to set it equal to mv squared over r. So if you solve this for r, a v will cancel off, and you will get mv over qb. So this is saying that a charged particle moving in a magnetic field will have a radius based on this equation. And since the force is always perpendicular to the velocity, it doesn't go faster. It always keeps the same speed. And because of that, it will always keep the same radius. So as say the proton enters, it will turn. And because the speed never changes, and the mass of the proton never changes, and the charge of the proton never changes, and the magnetic field never changes, all of these would give you the same radius. And so this thing would turn always having the same radius. So you would have a half a circle, and then it would exit the magnetic field and no more force, so it would go in a straight line. So this thing should form a little semicircle. It's not like at the beginning the radius is different than the end, so which would be, maybe something like a parabola where the amount of curvature changes. This says that the radius does not change. The only way to change the radius is to change the speed, or to change the particle, or to change the strength of the magnetic field. But for this problem, none of those change. Now, it's obvious that the mass and the charge doesn't change. I think it's pretty obvious that the magnetic field doesn't change. But the one that is maybe not so obvious is that it goes around in this semicircle, the velocity doesn't change. And that's where this whole idea of work and energy come into play. The work, when you have a force that is perpendicular to the direction it moves, you do zero work. And zero work means it doesn't gain any speed, which in this case, it doesn't gain any speed, it doesn't change its radius. And so I'll go back to page 1 to say, whatever speed it gained by being accelerated, which is what we got using conservation of energy, is now the same speed it will have as it goes all the way around. And of course, keeping that same speed, it would have the same radius, so it actually makes the path of a circle, or technically a semicircle. So that's the point I wanted to make. And in fact, your author actually worked out this equation in that same example I was showing you, example 3. And so maybe you could have even just started this whole problem right here, and you didn't have to go back and redo your physics 121. But I think it's good, right? Because 121 is a tough course, and it's good to see it a second time. Because most of the time people kind of learn it just superficially on the first time, and then they don't really get a deep understanding until they see the second time. I would say that about your calculus. You probably learned calculus, and thought you knew it well until you hit physics 121 or this class, and you're like, whoa, wait, how do I do this? And so now you're like being forced to really learn the calculus deeply. And that's what happens here with the physics 121 and the mechanics stuff. So we're back here to work in energy and force and cross products and conservation of energy, all these great things we saw the first time in 121. Let's apply them again. All right, so if we apply all that older physics 121 stuff together with our new force, this is what we come up with. All right, so now we're actually in a position to actually do the problem. So again, I hope I wasn't too long-winded. I was asking a group of students earlier today if I should be so long-winded and review all that, or should I just jump into the solution? And they encouraged me to say, okay, no, stay with that long-winded stuff. That's why we're asking. It's neat to know those details in the background. All right, so, and I'll continue to do that, I guess, unless you guys tell me to do otherwise here. But you probably could have started the problem right here. R equals mv over qb. That is the result of our long discussion of page 1 and page 2. And so if you apply this to the proton, so radius of proton, and you also apply it to the deuteron, so radius of deuteron, and you also apply it to the radius of the alpha particle. For the proton, you would put mass of proton times the velocity of the proton over the charge of the proton times the magnetic field. Now, filling in what we know, we'll just label the mass of the proton as m sub p. The charge of the proton, they told us, was E. The magnetic field is just B. And coming back, and I think this was page 1 right here, we would have then the velocity of the proton. So this would be the square root of 2, and the charge would be E, the delta V, and the mass of the proton. Now, if we try to simplify this, I'll do something along this lines, perhaps. It looks like there's a mass of the proton that is downstairs, but it's under the square root compared to that one. So if you imagine putting this mass of the proton inside of the square roots, we would have to write it as mass of proton squared to put it inside the square root. And likewise, if you imagine putting the charge E inside the square root, you would have to write it as E squared. So on the outside, you would be left with just the B, the 1 over B. Inside, you would still have the 2, but this mass of the proton with the one downstairs leaves just one more mass of proton upstairs. And the charge of the electron, or it's not the electron charge, which is the same as the proton, the E would cancel with one of the ones on the bottom. So you'd be left with one on the bottom, and then you would have the delta V. So they don't give us any numbers to work with, but that right there would be the radius of the proton. Okay, so let's try this same equation with the deuteron. Because the deuteron has twice the mass of the proton. It has the same charge as the proton. And then it has a velocity. I'll have to come over here and do this square root for the velocity of 2 times the charge. Here's the charge of the deuteron. The delta V divided by the mass of the deuteron, which is 2 MP. Okay, now if we go to simplify this, let's see, what will it look like? I'll leave the B alone. I guess I'll leave the 2 alone outside for a moment. But if I go inside of this square root, I'll cancel the 2's here for starters. And then the charge of the deuteron and the charge of this one, I would put it inside. That would be leave an E downstairs. The mass of the proton, well, what the deuteron is actually 2 times the mass of the proton, but I'm leaving the 2 out front. But the mass of the proton I'll bring inside, which of course makes it a square and cancels with that one. Then you have a delta V. And this looks an awful lot like that one, except this one has a square root of 2, and this one has a 2 out in front, which we could write it in this way. We could write it as the square root of 2 times the square root of 2. And so I'll put the 2 inside. So we have square root of 2 times square root of 2. That's that 2. We still have the B outside. We still got the mass of the proton. We still got the accelerating voltage, and we still got the charge of the electron. So this part right here is the same as what we got for the radius of the proton. So I guess I would say we have the square root of 2 times the radius of the proton. And so the deuteron, coming back in our picture and maybe using red color, would have a bigger radius, and it would look like this. And again, that's why this is often referred to as a mass spectrometer. Did you notice then that the proton lands here, but the deuteron lands further out? And so things with different mass got separated into different positions. And so it is spreading out. So you can send in all these different particles, and the lighter stuff lands over here, the medium stuff here, and the heavy stuff here. And you can separate your stuff into what it's made out of. Extremely useful in things like organic chemistry, where you know you have nitrogen and oxygen, hydrogens, and you're just not sure what the ratio is, or maybe you don't even know what they are. So you send them through a mass spectrometer and see what comes out. And then you can say, oh, I have this much nitrogen, and I have this much oxygen, and I have this much hydrogen, and I have this much, whatever else might be in that compound. So it's a good experimental tool. All right, well, let me keep going here. Let's apply this to the alpha particle. So same equation applied to the alpha particle. All right, so what's the mass of the alpha particle? Well, we said that was 4 times the proton's mass, okay? What's the charge of the alpha particle? Well, we said that was 2 times the basic fundamental charge of the proton or electron. Then the B. Then what is the velocity? Well, the velocity of the alpha particle, I'm coming back here to this page 1 again, okay, would be the square root of 2 times the charge, which is 2e for the alpha particle, the delta V, over the mass, which we said is 4 times the mass of the proton. Now, if we simplify this just a little bit, the 2 and the 4 leaves a 2 on the outside. And in this square root, the 2 2's in top make a 4, which cancel with that one. So we've got E delta V over mass of the proton. And if you step back, this is really exactly what we had up here for the deuteron. See, the deuteron's got a 2 out here, which we got the 2 because a 4 canceled with the 2. And they've got inside the square root canceling of the 2's. We got canceling of the 4's. So if we did the same mathematical steps, we would end up with the same result. And so the deuteron and the proton each have the same radius. So the deuteron and the alpha particle are actually kind of a pain, I guess. I can use that word, because they would actually follow the same path. And they would, of course, because the alpha particle has twice the mass, which you would have thought it went further out, but it also has twice the charge that brings it back in. So that's why the deuteron and the alpha particle follow the same radius. And so if you're trying to build a spectrometer here, you can't tell the difference between an alpha particle and a deuteron. Although there are some things you can do, and the best thing to do in a situation like this is to make sure that the alpha particle gains 1 electron before it goes through. So now you don't have the same charge. And then they all have the same charge, but different masses, and they will spread out. So I should have emphasized that this mass spectrometer only works well if they all have the same charge. Therefore, the heavier ones will spread out over here. I hope that makes sense. Let me check the answer, because there was something I kind of questioned back here at the beginning. What number did we say this was? 11. And they got square root of 2 also. Okay. Yep. So they got both of them, the alpha particle and the deuteron, each having the same radius, and each of those being square root of 2 bigger than the proton one. Nice. All right. Wow. Well, I talked a long time. Hopefully that didn't get in the way of other questions, but was hopefully also enlightening. All right. Joshua, so you asked what problem it was. Good. So I'm glad you can kind of follow along there. That was number 11. All right. Well, I'm scanning the chat. I don't see any of you throwing anything in the chat. So, Lisette, are you still here and in earshot? Oh, good. You shot something at me. Problem number 6 on the homework quiz. Okay, good. Let me write this down. 121. Problem number 6. So number. All right, let's see. Let me come back over here to here is your assignment. And it's loading, a little slow here for some reason. And there are, okay, so quizzes, conservation of energy is the latest one. So I think you're talking about that one. And number, maybe not. Am I doing something wrong? Help me out. I only see 5 problems on the quiz for conservation of energy. Maybe I'm on the wrong one. Right?
Yeah, it's the homework quiz, not the weekly quiz.
Oh, okay. Yeah, good. Yeah. Because now, and I was going to look on a due date. Yeah, I shouldn't do the quiz for you. So I should do the homework quiz though. I think that's allowable, right?
Yes, I haven't done the weekly quiz yet.
Yeah. Okay. Okay. So let's see. What do you guys have? You have. How does this work? You have reading quizzes, and then you have lab, homework, and weekly quiz. Oh, okay. So homework quiz. Let me try that one. Homework. And that one. Yes, and that one does have a number 6. Nice. Okay, so let me write down a time here. It is 1:23. Okay, and let's see. The title. You guys don't really have number. Well, I guess you do have number 6 on that quiz, but your instructor gives it the title elastic energy and gravitational potential energy. Good. All right, now maybe the first thing I should say is this particular section is called the principle of conservation of energy. And what that means is whatever energy you start with plus whatever energy you add to it is equal to what you end with. And I think for most people that kind of makes sense. It's like, okay, if I started my savings account with, say, X amount of dollars, and then during the next month, I add to it Y amount of dollars, at the end of the month, I then have a number that equals the sum of those two. That's what we mean by the conservation of energy. So I like to encourage students to do kind of a split of their piece of paper. And maybe on this side, say, all right, this is the before, and the other side is the after. You'll see that in symbol forms that look something like this. So before, you might add up all your energies. So maybe you have a kinetic energy. That's initial. You might have then some potential energies that are initial. And in this case, there are 2 kinds. There is the elastic energy, which is the energy in a spring. And then there's also the gravitational So both of those are fitting into this category. Then you might have some non-conservative work. That's what I meant here in my kind of my savings account, that, okay, this is what I start with and this is what I add. And so we might actually do some pushing and pulling. And so this is force times distance, or more appropriately, force integrated with distance. And so that has to equal all the energies you end with at the end of the month. So this would be final kinetic energy plus your final potential energy. So one of your tools is conservation of energy, and this is it. And if this helps you, know that all of the problems on this homework quiz and all of the problems on the weekly quiz probably start right here. Now, maybe they're a subset, like they only have you do the conservative, the work by the conservative force, or maybe they only ask for the kinetic energy. So maybe it's not a full thing, but this is the full conservation of energy. So watch what happens here. Kind of drawing this problem, it says, a pinball testing machine shown in the ball of mass M. And so there's a little spring here, and then a ball of mass M is launched by a spring with a spring constant of K that has an initial compressed distance of X. And so you push it back the distance X. The ball slides along a surface with some friction. So it kind of slides along for a distance D. And maybe I'll make it kind of a rough surface. So it has a coefficient of friction. The ball then, it looks like the surface goes uphill. As the ball then goes uphill, reaching a maximum height of H. During the whole process, friction does a negative amount of this non-conservative work. Okay, so we'll talk about that. And then it looks like what's given, the mass of the ball at 78.8 grams, the spring constant at 787 newtons per meter, the distance compressed 3.51 centimeters, the height, it goes up 21 centimeters. And the question is, how much work is done by the conservative force? Now, the problem even helps us out by saying it's going to be a negative number. All right, so it says the friction does a negative amount. So we're going to find this, and hopefully we're going to get a negative number. Okay. Now, I'll also say that, going back to my analogy, I guess that would be like saying you start with X dollars in your savings account, and then you add a negative amount. So instead of actually adding anything to your savings account, you're actually taking something out. Maybe your computer broke and you're like, oh, bummer, this month I better take some out because I need to buy a computer to stay in class. So you have a negative number here. But again, if you add a negative number, then it's still equal to your total. So it doesn't change the principle of conservation of energy, whether this is a positive or a negative. Just like the principle of money, you just add them together. You're just adding a negative number, and you end up at the end of the month with less money in your savings account than you started because you added a negative number. So it's okay if we get a negative number. Our work can be positive or negative or zero. But anyways, so let me call this page 1. And now that I've kind of gone through the problem, and I think more importantly, the principle of this, let's start filling this in. And so as I come over here to page 2, let me come back to what I always like to do for problems like this and encourage students to do the same, is to say, all right, over here is all my initial stuff. That's initial energy plus non-conservative work. That has to then equal my final. All right, so let's come back over here and say, all right, let's start here. What is my initial kinetic energy? Well, maybe down here on page 1, I better write out a formula for the kinetic energy, 1/2 mv squared. I'll also put a formula for what we call the gravitational potential energy. And I'll also put a formula that we call the elastic energy of our spring. So I'm going to need these 3 in the problem. Okay, actually, I don't even think I'll need this one, but let's see. So starting back here, how much initial kinetic energy do I have? Well, we're starting from the ball compressed and the ball at rest, 0 velocity. 0 velocity would mean 0 kinetic energy. Okay. Now, how much initial potential energy do I have? And also keep in mind that there's 2 ways to store potential energy. One is based upon height, that's in the gravitational force, and another one is how much a spring is compressed. So that's an elastic force, okay? And for this problem, I would call then the ball starting at a height of 0. So when it comes to this term, the gravitational potential energy at a height of 0, I would put 0. But the other term right here, the elastic energy, the spring is compressed. And that's what this X is. This X is either the distance you compress the spring or it's the distance you stretch the spring. Either way stores energy. You can imagine if you compress a spring, then it wants to snap back. If you stretch a spring, again, it wants to snap back. So it doesn't really matter whether you compress it or stretch it, the X is the same. And hence the square. So it doesn't matter if X is positive or negative, you square it, you get the same amount of energy, either compressing it or stretching it. All right. So in this problem, we are compressing it. So there is energy stored in the spring, and that would be 1/2 kx initial squared. I'll put in my numbers because we do know those numbers. I'll put them in here in just a second. But I just wanted to write that out. And then, of course, plus the non-conservative work. So that's this side of this little table. That is taking the kinetic energy, 0, the 2 potential energies, 1, 0, and the elastic non-zero. And then the other one is the frictional energy, or the non-conservative one, the one we're looking for, this rubbing going on. And then that has to equal to the energy on the other side. All right, so let's talk about the other side. Now, the other side, it rolls up the hill and comes to a stop. Stop's important because the kinetic energy is one of the energies I have to add. And that formula for kinetic energy is based upon its speed, and its speed is 0. And so I would put a 0 for its kinetic energy. That's why I kind of said while I was doing this that we really don't even have to worry about the kinetic energy because it doesn't change. It starts at 0, finishes at 0. So it's the same on both sides. But it's kind of nice to see that what they are for other problems. It may not be 0 on both sides. This one it is. Now, as it rolls up the hill, it now has some height h. So its gravitational potential energy, this term right here, what is its final potential energy, would have a term mgh. Now, also remember, potential energy has two pieces. It has a gravitational potential and the elastic one. But at this point, once the ball leaves and goes up, the spring has gone back to its what we call its natural length. It has snapped back. That's what pushed the ball. So the spring is no longer compressed or stretched. It's back at a distance of 0 for x. So in this little formula for the elastic potential energy of the spring, we would have a 0. So I'll put a 0 there. So this is what I was saying is you could start every problem with this, but a lot of these are zeros. And so you know, this might, be, you try to talk about all of them, it's extra hard, but while you guys are asking the question, I thought I better talk about every single one. And so like you can see, 1, 2, 3, 4 of these are zeros. I didn't even really need to include those. So this is really saying that the elastic energy that you start with, then adding a negative number, so taking some energy away because of the friction, that would be heat. Then it goes to the gravitational potential. So that's what it's saying. This is what you start with. Then you lose some. And at the end of the month, this is what you're left with. And that energy is now in the form of a height. And so we went from energy stored in the spring to energy stored in the height of the ball. I guess this kind of might be like what we do a lot in California, kind of the reverse. We've got a lot of energy stored based on height for water because it snows up in the high Sierras. And so there's a lot of gravitational potential energy. And so we use that water coming down to make electrical energy. Now, it's too early in your 121 education to talk about electrical energy, but that's what we're doing now in the 122 class. And so we convert it from a gravitational potential energy into an electrical energy. This one's kind of the reverse. It's changing it from an elastic energy that makes it go to a kinetic energy, which then makes it go into a gravitational potential energy. So it finishes with gravitational. In fact, maybe a good example of that is kind of these new solar arrays that they're doing. They got so much sunshine during the daytime that they use that electricity in a crane, and they take the crane and they lift heavy blocks up a hill and set it down. That way at nighttime, when there is no more sunshine to make our electricity, they'll take that big heavy block on top of the hill and hook it to that same crane. And now the crane will go down and it will turn a turbine as the big heavy block goes down at night. And so you can still generate electricity even though the sun's gone down by storing it as gravitational potential energy during the day. So maybe, but then no spring is involved. Anyways, maybe I'm just saying too much. Forgive me. Okay, so let's actually now put in our numbers. So if I put in a 1/2, and so here's our K, where was our K? 787 newtons per meter. Now let me pause right here because I know, Lisette, you had asked me about, you were having troubles with units. And here's a good example of that, because I have the K in newtons per meter, but then I'm going to multiply by an X, and the X is in centimeters. And if I put it in as centimeters, I'm not going to get centimeters to cancel off with the meters. And so it would be much better here, and I can see it right here, that I would want this X to be in meters so they cancel. Now there's two of them because it's squared, but that would be perfect because one of the meters would cancel off, leaving just one. And then I would have a Newton times a meter, which is what the definition of a joule is. And since we're talking about energy, energy is in joules, and buried inside of a joule is a Newton meter, and those are each in meters, that's my clue to say I should do things in meters. And also what I told you while we were Zooming is, oh no, I think it was on the phone. Oh no, maybe I'm confusing you with another student. Never mind. I think I am confusing you with those. My apologies. Yes, my apologies. I was Zooming with somebody who's having trouble with it. So, but let me do the units just in case anybody else is having troubles. Okay, so I'm going to put this 0.0351 meters squared. Okay. Okay. That then would be the distance in meters. And I'll say it again for anybody who might have troubles with this, that the reason I know to do this in meters is twofold. One, I need a meter up here to cancel with the meter down there. And the other one is I know that this is talking about energy. Energy is in joules, and buried inside of a joule is a Newton and a meter. So I want this to be in meters because of that. Now this term is what we're looking for. So there's the non-conservative work. And then on this side of the equation is the mass. Now, let me point out the same unit issue. Under the mass, they have 78.8 grams. But again, if I'm calculating energy, energy is measured in joules. A joule is a Newton times a meter, and inside a Newton is a kilogram. So that's my clue to say, careful with the units. You want to put your mass in units of kilograms so that the energy will come out in joules. G is the 9.8 meters per second squared. And the H, the same idea. The problem gave me the H in centimeters. But again, like we did for the mass, we know that we want our energy in joules, and buried inside of the joule is meters as well as kilograms. So we want mass in kilograms and distances in meters. So this over here, if I can just squeeze it in, would be 0.21 meters. All right, so finally, I can get my calculator and say, all right, so I've got 1/2 times 787 times 0.0351 squared. And so we're looking at 0.485. And just to confirm it's joules, watch this meter would cancel with one of them, right? Remember, it would be meters squared. So one of them is going to cancel. So I still have a meter, and that meter times that Newton is the definition of a joule, a Newton times a meter. Okay, so that's the energy that I start with in compressed spring. This is the elastic energy of this compressed spring. Then plus what's going to be a negative number. So we're going to finish with a little bit less. So let's see how much that little bit less is. 0.0788, 9.8, and 0.21. So this is 0.162. And again, looking carefully at the units, I already did convert it to kilograms because that right here, kilogram meter per second squared, that right there would be a Newton. And then that Newton times that meter, Newton meter is the joule. So I would have run into troubles if I didn't convert grams to kilograms or centimeters into meters. All right, so finally, we can get the answer here, which would be to take that first number and subtract, go up there and copy and paste that number. And so we're looking at a minus 0.323 joules. So that's how much energy was taken away from the pinball and would show up as rubbing and heat. And so the ground that it rubs on would be a little warm, and for that matter, the ball would be a little warm. And that's the whole reason it didn't go up very high. It could have gone up much higher if it didn't have this right here, this rubbing going on. All right. Hope that helped. Oh, I should check my answer. Did I get the same number? No, they get a 314. Normally I would say that was just some rounding. Seven. Yeah, I think it's just a little rounding. Okay. Everything seems good. All right. Good. All right. Let me put those aside and I'll head back over to the chat here and see if there's anything more. All right. All right, Brendan, we're going to go into, this one, let me figure out, yeah. Was drawing a blank there on what class you're in, but you're in 122. So I assume you're talking about chapter 29 and then number 16.
Oh, just a question. So I saw on the pages you post with all the homework questions on them, there was like 2 pages with all the questions in order, and then like a 3rd page with all of these numbers that were like in a different order, not lined up. And I checked the syllabus, and the first 2 pages match up with that, and then the 3rd page it just seemed like it was random questions. I'm not sure if that was just like extra practice problems you posted or something, or
yeah, I should send this again. About 2 weeks ago, I sent you a little note that said,
oh yeah,
the first page of 30 is missing.
okay.
So yeah, on the homework, chapter 29 has 2 pages, and that's the end.
Oh, so that's the second one for number 30 then.
Yes, exactly.
Gotcha. Okay.
Yeah.
That makes sense.
And that's why they look out of order. Yeah, I should remind everybody of that, especially as they, because they could start doing those. And if you start doing that 3rd page, which is really from chapter 30, you're going to go, what? How do I do this? Yeah.
Okay, good to know. Thank you.
Okay. All right. So I'll get started on this. And Lisette, you are more than welcome. I see you saying thank you. And then, throw another one up there if you want. Hang on, and I'll get to yours when we're done here. Or you can come back after. Looks like our break's not too far away. So we'll come back at 3 after our break. All right. So Brendan here. Let's go back to your guys' questions. And number 16 says this. Assume the region to the right of a certain vertical plane contain a vertical magnetic field of magnitude 1 millitesla and a field of 0 in the region to the left of the plane. Oh, okay. So I'm going to maybe do something like this. So over here, and then over here. So there's two regions. Assume that the region to the right, okay, has a vertical magnetic field. And so if we go back to the problem we were doing before, which I guess was number 11, I'll come back to that picture. It's really kind of the same thing. In fact, didn't this follow number 11? Yeah, so we're kind of in the same thinking category here, that this area has a magnetic field, which I will label in green with a dot, meaning the magnetic field is coming up towards the screen. Okay. They say vertical, and sometimes vertical is kind of hard to kind of draw, because sometimes we draw vertical going up on the paper, and sometimes vertical, like we're writing on a desk, we draw vertical coming up out of the screen. And so I'm going to do that. So when they say, assume that the region to right of a certain vertical plane contained a vertical magnetic field. Let me be careful, since they use vertical for the plane and the field, maybe I should make them in the same direction, because I don't have the plane. Or maybe if you talk about the normal to the plane, they are. Okay, so the normal to the plane is vertical, coming towards the screen, and the magnetic field is vertical, coming towards the magnetic. Let me keep reading, but I think that's it. Sometimes you got to read these a few times to get a real understanding of what they're asking. All right, and the field value we know. They say it is 1 millitesla. Okay, and the field is 0 outside. So over here, the magnetic field is 0. So again, that is identical to what we were doing in this number 11 one, where we said they would go straight because there's no force on them. Then they would enter a magnetic field, and they would follow this half circle with this radius. Okay. So if an electron is originally traveling perpendicular to the boundary plane, and it passes into the region of the field. All right, so again, this is sounding a lot like the one we just did in 11. Of course, we had protons, deuterons, and alpha particles in this one. Here they say an electron. So I'm going to just put a direction of V for velocity, and I'm going to put E with a minus sign for the electron. And so here's the electron approaching this region. So an electron originally traveling perpendicular to the boundary plane passes into the region of the field. Okay, A. Determine the time interval required for the electron to leave the field region, noting that its path is in a semicircle. All right, so maybe without going through all these great details that I did before, since you guys already saw me talk about this in 11, but anybody who maybe just jumps into this problem, let me encourage you, go back a little bit in this video, because we did, before we did this 121 problem with the elastic, we did number 11, and we came up with two important things. Number one, this is the velocity if you accelerate it. I don't know if we'll need that for this problem, but this page 2 was this, where we argued that a charged particle would bend, and because of this equation, we argued that it would be something of a constant radius. So it would be a semicircle. Okay. And of course, they even help us out by, they say, noting that this path would be in a semicircle. So we don't have to prove that it's a semicircle, but it would. And in this case, since it's an electron, I believe it's going to go up instead of down. Let me just run through that again. So let's take a look at the force on a moving charge. in a magnetic field. And I'll start with the cross product. You put your fingers in the direction of the first one and you close towards B. So I'm going to stand up here and put my fingers like this. And this wouldn't quite work. This would have my fingers in the direction of V, but when I close them, I'm not closing them towards B. And so I need to do this. So V cross B is down. Remember, these are electrons, so they have a negative charge. So this part right here, V cross B, is down, but then I am multiplying by a negative number here. So the negative of down is up. And so this negative charge would make a semicircle like that. The magnetic force would start to be up. And again, the same argument that we used in problem 11 would be that because the force is perpendicular to the velocity, it doesn't do any work. Because it doesn't do any work, speed doesn't change. And because the speed doesn't change, the radius doesn't change. And so this is not a path of a parabola or a hyperbola or anything else that changes. It is actually a circle. It is something of constant radius, because we're going to have a constant velocity, a constant mass, a constant charge, and a constant magnetic field. All these are constant, making the radius constant. And now it just curves up. So positive objects curve down, negative objects curve up, each making a half a circle. Okay, so now this problem says determine the time interval to the electron to leave. So they're basically saying how much time does it take to go this half circle? Okay, well, let me remind you that the distance something travels is equal to velocity times time. I guess you could also say plus 1/2 AT squared, going back to constant acceleration problems. We could integrate it, but what the bottom line is, if you don't have an acceleration, and I should be careful here, we have an acceleration based on turning, but we don't have an acceleration based on speed. So if you don't have a tangential acceleration, then this is our answer. Distance traveled equals to velocity times time. Okay. So how far does it travel? Well, it travels a half a circle. So I'm going to put 1/2 of a half circle. Well, a half circle is 2 pi r, or well, full circle is 2 pi r. So 1/2 of a full circle is the distance it travels. Now, its velocity, and this is where I'm going to use this equation, would come back and solve this for velocity. I'm going to move the Q and the B to the other side. So this would be a Q, a B, and an R, and I'll divide by M. And then that would be the velocity. And then that would be the time. And so that's what I'm looking for, that T. So I could cancel off the 2's, and it looks like I could also cancel off the R's. And so the time would be, looks like I would still have a pi over here, have an M, and I would divide then by, and since they said electron, I should probably put an E for the charge of the electron. So instead of the Q, I'll put the E and then a B. And so this, I think, is actually as far as we can go. They don't give us any numbers to punch in. Determine the time interval required for the electron to leave, noting that the path is a semicircle. Now, how come they have some numbers here? Maybe I better come back and keep reading because they have some numbers. Find the kinetic energy of the electron, assuming, here they give me some information. that the maximum depth penetrated is 2 centimeters. Okay, so if you come back to this formula, and so maybe it'd be better to try to calculate B first, because coming back to this picture, the distance it penetrates would actually be the radius. So they used some fancy words there to make you have to realize that the deepest it goes is the radius. So if I write this as a R equals mv over EB, okay, where E now, so here we go, this equation, I could now use that to get velocity. Okay. Oh, wait. I was thinking I had to do B before A. I'm sorry. There's no velocity in here. We don't need to do. Let me put a pause on B. I'll come back to it. But we could actually then calculate this because they said it was an electron and they gave us the magnetic field. So we do know these. All right. So pi, we know 3.14. Mass of the electron, 9.11 times 10 to the negative 31. Charge of the electron, 1.602 times 10 to the negative 19. And magnetic field is 1 millitesla. All right. So yes, I can actually calculate here A. So 3.14 times 9.11 times 10 to the negative 31 divided by 1.602 times 10 to the negative 19, and that all divided by 1,000 equals a time interval, time interval of 79 times 10 to the 8th. And that would be in seconds. I suppose I could write this as 17.9 nanoseconds. And now I can go on to B. All right. So now B said what? Kinetic energy. Find the kinetic energy of this electron. All right. So again, they've given me the ability to find the velocity because of this equation. And so now I can get the velocity. Maybe I'll go on to another page here, page 2. But velocity then would be the charge, 1.602 times 10 to the negative 19, times the magnetic field, 0.001, times the radius, which is the 2 centimeters, so 0.02 meters, over the mass, 9.11 times 10 to the negative 31. Okay, so 1.602 times 10 to the negative 19, 0.001, 0.02, divided by 9.11 times 10 to the negative 31. And we are looking at 3.52 times 10 to the 6 meters per second. So that'd be 3.5 million meters per second. So really fast, although not that fast compared to the speed of light. So those of you who've gone through 123, we don't have to worry about the relativistic effects Of course, that's why the time is so small, only 17, close to 18 nanoseconds to make the half circle. So really, really fast. And the main step is the kinetic energy, 1/2 mv squared. So its mass is 9.11 times 10 to the negative 31. And its speed is the 3.52 million meters per second. So then I can get out my calculator, and in fact, I already have the speed in there. So I'm just going to hit square and go backwards, times 9.11 times 10 to the negative 31, and then times the 1/2. And I get an energy of 5.63 times 10 to the minus 18 joules. And we probably could stop there. But when we start dealing with little things like electrons, it's nice to introduce another unit of energy. So in Physics 121, doing our mechanics, joules was very convenient. But here in our electronics, especially when we're doing individual particles, a joule is just way too much energy. So we have another unit of energy. It's called an electron volt. It's equal to 1.602 times 10 to the minus 19 joules. So it's a really small amount of energy. And it's often very useful to use it when we're talking about these moving particles like protons and electrons. And so we like to do things in electron volts. Now, as the name implies, here's where it comes from. If you took an electron, and let's say the electron is between a capacitor where one plate is positive and the other plate is, well, one is positive, one is negative. And so it's close to the negative plate, and it shoots across. And you charge these plates just enough so that the voltage difference is 1 volt. To calculate the energy, we would go Q times V. Remember, the Q is the charge. So 1.602 times 10 to the minus 19. And the voltage change is 1 volt. So when you multiply the charge of the electron times the voltage, you would say that the electron gained a kinetic energy of 1.602 times 10 to the minus 19 joules. And we like to then call this an electron volt. This energy right here is the energy you get when you take one electron and you let it go and accelerate by 1 volt. Hence the name, an electron volt. One electron being pushed through a capacitor of 1 volt. So I'm going to use this conversion factor because I bet when I look at the answers, the author does. And again, it's just kind of common to use units of electron volts because, again, joules are just too big. I mean, look at that, times 10 to the minus 18. So let me take this number, 5.63 times 10 to the minus 18 joules, and multiply it by the conversion factor, which is 1 electron volt is equal to 1.602 times 10 to the minus 19 joules. So this would be like converting centimeters to meters, or converting inches into feet, or liters into gallons. You just got to know what the conversion factor is. And when you write a number on top and the same number on the bottom, so these are the same, electron volt is the same as 1.602 times 10 to the minus 19 joules. This is just a 1. So you're not changing the number, but you are changing the units. So this is going to convert it into a unit that's probably new to a lot of you, called an electron volt. So I'm going to take that and then divide it by 1.602 times 10 to the negative 19 and get 35.2 electron volts. And so dealing with the kinetic energy, probably best to label it as 35.2 electron volts, but certainly nothing is wrong with labeling it as 5.63 times 10 to the minus 8 joules either. That would be fine. Good, and I'm going to check the answer, and yeah, looks like they did do it in electron volts. Good. All right. All right, Brandon, hope that helped. Looks like it's past our break time, so I'll see you in about 49 minutes again if you come on back, and we'll take more questions for you, okay?
Yep.
All right.